Hey everyone, welcome back and let's write some more neat code today. So today let's solve binary tree right side view. The problem is pretty self-explanatory. We're given a binary tree and basically imagine you're standing on the right side of it. So this is the tree. Imagine we have a person standing over here, right? You can see from the right side, you can see everything on the right side. And so what nodes can this person see? Well, they can see the root node, right? There's nothing blocking that. They can see this node. Can they see 2? Well, you can't really see 2 because it's behind this node, right? It's basically blocking this node, right? And the same thing with these two nodes, right? We can see 4 because it's the rightmost, right? Like imagine the person sees this, but you can't really see that because it's being blocked by the 4. So when you just look at this example, this problem seems really easy, right? So your first thought might just be, okay, start at the root and keep going to the right, right? Just keep going down and we'll get the right side view, right? Every node on the right side. But we can make a counterexample pretty easily to show that that actually won't always work. Imagine this node 5 had a left child, right? Like let's say it has 7 over here. Now you can see that our result is going to be 1, 3, 4. We can't include these nodes because they're being blocked, but there's nothing over here, right? The 7 is not being blocked. So if this was our input tree, then our output would be 1, 3, 4, and we'd have to add a 7 to that because look at our person, they can technically see down here. So basically what this means is we can't only look at the right children, right? So you can actually solve this problem with a breadth first search. I know most tree problems you can just do depth first search, but this problem can actually be solved with breadth first search. There actually is a depth first search solution, but I'm going to explain the breadth first search solution to you because in some ways it's easier. And you might know breadth first search in a tree is also known as level order traversal. So it's also known as level order traversal, which you're going to see why it's called that just about now. So instead of saying that there's a person over here that can see only the right side of the tree, another way of framing this problem is saying, okay, for each level, right, each level of the tree, we want the rightmost node. So the first level, it's pretty easy because there's only one node. So we'll just take the 1 from that. What about this level, right? We look at the nodes together. For this level, we want the rightmost, so we get the 3. Next, we want the third level, and what's the rightmost value? It's going to be the 4, right? And lastly, we take the last level, and there's only one node, it's 7, so we're going to get the 7. So with a picture, this is pretty obvious, right? It's really easy to know what we're doing with a picture, but actually writing the code for level order traversal is a little bit tricky, and I'm going to show you how to do that. Basically, how we're going to implement this is with a queue data structure. So initially, what we're going to do is add the root node to our queue. So we're going to add 1 to our queue. And we're also going to have a result array. So now what we're going to do is take a look at our rightmost value in the queue. It's 1. So we're going to add 1 to our result. Next, now we're no longer looking at this node, we are looking at its children, basically the next level. So we can get that by taking the left and right child and adding them to our queue and removing the leftmost value from our queue. So we add the 2 and the 3 to the queue, and it's important that we do it in order, right? The left and right, the left has to be added first and then the right, because we always want to get the rightmost value when we add to our result. So now this is the second level of our tree, right? So what are we going to do? Again, we're just going to take the rightmost value, in this case it's 3, add it to our result. And next what we're going to do is we're going to look at the leftmost value, pop it, right? But before we pop it, we want to take its children, our tree, right? So what are we going to do? Again, we're just going to take the rightmost value, in this case it's 3, add it to our result. And next what we're going to do is we're going to look at the leftmost value, pop it, right? But before we pop it, we want to take its children. Notice it doesn't have a left child, right? That's null. And the right child is 5. So we're going to take its children and add them to the queue. So now we're adding 5 to the queue. So we're done with 2. Next, we have to remove 3 from our queue because we're done with this level. We want to look at the next level. So we remove 3, but before we remove 3, we have to add its left and right child. Notice it doesn't have a left child, but it has a right child, 4, so we're going to add 4 to our queue. So now look at our queue. We have 2 elements, and these 2 elements represent the third level. So what we're going to do now is take the rightmost value once again in our queue and add it to our result, because that's the rightmost value in this level of the tree. And now we're going to repeat that process. So for 5, we're done looking at 5, but we have to look at its left and right child. It has one child, 7. So we remove 5 and we add 7 to our queue. And we also look at 4, so we're done looking at 4, right? So we pop it, but before we pop it, we want to look at its children. Notice both of the children are null, so basically we've reached our base case. We don't end up adding more elements to the queue in this case. And now there's only a single element remaining in our queue, and that element represents the 4th level of our tree, and the rightmost node in that level is 7, so we can add 7 to our result. And we still have to remove 7 now, right? So remove 7 from our queue. Notice it didn't have any children, right? Both of the children were null. So we've reached our base case. We cannot add any more elements to the queue. Therefore, the queue is now empty. So now we can stop running our algorithm. We know that our result is complete. We have no more nodes left to traverse. So now let's translate this into code. So I'm going to initialize a empty result. I'm also going to have a queue, so in Python we can do that like this. It's called a deck, and I'm going to initialize it just like I did in the picture with a single element, and that's going to be root. Now it's possible that root could be null, so technically it's possible that our queue could have null values, and I'm going to show you how I'm going to handle that. So while the queue is non-empty, that means we can pop elements from the queue. So I'm going to get the right side element from this current level. I'm initially going to set it to null, and I'm going to get the current queue length, right? The current length of the queue. So right now, imagine it's just a single level, right? Our queue at any given point contains one level at a time. So for this level, I'm going to get the length. And then what I'm going to do is go through every element in this level. So for only queue length, right? The initial length, because we know this queue is going to continuously be updated. So I'm going to go through every element and I'm going to pop it. So queue pop left, right? We know we're popping elements from the left and we're adding elements to the right. Now we know the node actually could be null. So what I'm going to check is if node is not null. If it is null, then we can just go to the next iteration of the loop. So if it's not null, what I'm going to do is update our right side to that node. So you can see that after this entire loop is done executing, what right side is going to have is the last node that was in this current level of the queue. And since this node is not null, I'm just going to take its children, so node.left, and I'm going to append that to our queue. And also I'm going to take node.right and append it to the queue. Now it's technically possible that these children could be null, but we know that if they are in the next iteration of the while loop, we'll come back here and we'll verify that the nodes are non-null before we update our right side. And it's also important that you add the left node before you add the right node. And after this for loop is done executing, what we have done is taken every node in the current level, popped it, right? That's what the pop is doing, and taken all the children of that level and added them to the queue. So basically what we've done is removed the elements from the previous level and added the elements from the next level. So that's good. And the other thing that we did is we took the right side, the rightmost node in that level, and had it stored in the right side variable. So now we can take to our result, we can take that right side variable and append it to the result. But not just right side, we actually want right side dot value because we're trying to append the values. And it's actually technically possible. Initially, right side was null. In one of the base cases, the right side could actually be null once we've reached the last level. So we're going to verify that right side is non-null. So once we've done that, and once this queue is empty, meaning we've gone through every single level of the tree, then all we have to do is return our result. So there it is. It's a pretty efficient solution, even though this percentage doesn't indicate that. So I hope this was helpful. If you enjoyed, like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon.